For section 3 of chapter 5, we'll look at how we can find the probability of a certain number of successes in trials of a binomial experiment. So I know we've been talking about probability since chapter 4 in unit 2, and we continue to discuss probability in unit 3 with chapter 5 and chapter 6, but we are approaching probability with different types of problems. So in 5.3, we look at a certain type of probability that's modeled by a binomial distribution. And so in chapter 5, you're introduced to new distributions, and in chapter 6, you'll also be introduced to a new distribution that we can use to help us kind of find probability and discuss probability in a differently than we did in chapter 4. So first, let's talk about what a binomial distribution is. So in a binomial experiment, we look at the probability of the experiment satisfies these 4 conditions. Now in your homework, you won't have to confirm these 4 conditions, but these are things that we want to be considering as we work problems in section 3 of chapter 5, how they satisfy these 4 conditions. So any type of application of the binomial distribution, we look at a fixed number of trials. So whatever the experiment that we are looking at, it has a finite number of options or a finite number of outcomes. That's where the fixed number of trials come in. Each trial, for one, is independent of each other, and each trial has 2 outcomes. The outcome can either be a success or a failure. And then the probability of achieving a success is the same for each trial. And so when we look at some more application problems of the binomial distribution through the binomial experiment, then we can kind of run through these 4 requirements in more detail when we look at an actual a problem. After we kind of talk about, you'll be introduced to something new in chapter 5.3, which is reading a table. And then I'm also going to show you a formula that does the same thing as the table, but the table can only be used certain times. The formula can be used all the time, so we'll talk about that. So in our first example here, we want to compute the probability of X successes using table B, and table B is a probability table only for the binomial distribution. Now in the video, you can't get to this table from here, but if you go to eCampus, so if I click out of here really quick, if you go to eCampus and you navigate to unit 3 and you find where it says chapter 5, section 5.3, click on table B. It's 6 pages, so I wouldn't advise printing it off, and you'll only need it for this section. And you can go through this table, and I'll tell you how to use this table in this video lecture. So let me go back. And so what we would like to do is utilize the table to help us calculate different probabilities. Now, this table can only be used for certain values. For one, it only goes up for 20 when n is 20, or when the number of trials is 20. So if you have 25 trials or 50 trials, then you can't use the table. So that's the first value here, is the number of trials. P represents the probability of a successful event occurring. So in the first example here, in 2 trials, if you look at the very top row of the table, this is the probability of a successful event occurring. So if this value 0.30 is in the table, which is here, then I can use the table to calculate the probability. But I'm also going to show you how to utilize the formula, because you can utilize the formula as well to arrive at the same value. Sometimes the table is a lot easier because you can go directly to the answer you're looking for, and sometimes the formula works just as well. The formula works just the same. So this first example wants to know, compute the probability of 1 success out of 2 trials if the probability of a success is 30%. So there's a 30% chance of having a successful outcome. And so what we would like to calculate, in an event that has 2 trials, what's the likeliness of there being 1 success out of those 2 trials? So when we kind of break down this table, n is the number of trials again, x is the number of successes. So we have a probability table for no successes, 1 success, and 2 successes. So in this case, since the probability of a success is 0.3 or 0.30, so 30%, then the likeliness of there being 1 success out of 2 is 0.42. That would be my probability here. Using the table, of course. And I'm also going to show you how we would utilize the formula as well. So that's how you would utilize the table with the information provided. Much like in your homework, it's going to give you a value for n, which is the number of successes, a value for p, which is the probability of a success, and then a value for x. The value for n is the number of trials. The value for p is the probability of success, and the value for x is the number of successes we're looking for, the probability for that outcome. So let's look at another example. With number 2, so I've just kind of screenshotted the parts of the table that I want until I couldn't fit it anymore in my document, and then I'll go back to the actual table itself. But for this one, we want to look at, well, what's the probability of 3 successes when we have 4 trials, and the probability of a success is 60% or 0.60. So we'll go to n equals 4. These are all the different outcomes you could get. You could have no successes, 1 success, 2 success, or 3 successes. And we want 3 successes, so I go all the way over to 0.6. And this is the probability that there are 3 successful outcomes in a binomial experiment that has 4 trials where the probability of a success is 0.60. So that would be my probability. Now, what we wouldn't be able to, well, we could still find this information here from the table. I just don't have the table because I want to go and look at the table now, the one that you're going to pull up from eCampus. So now I want the probability of no successes when there are 5 trials and the probability of a success is 0.10. So if I go to my table here, I need to find 5. So here's my 5, and then I want no successes, so that's 0, and I want 0.10, so 0.590 would be the probability that we're looking at. So I go back, the probability of no successes is 0.590. And similarly with the last example, what's the probability of 4 successes in a binomial experiment of 10 trials with a probability of a success for each trial is 0.40. Well, if I go to that table, so I'll scroll down, so 10 trials, 4 successes, and we go over to 0.40, so that would be here, 0.251. And so this is just utilizing the table to compute a probability for conditions that satisfy a binomial distribution, which is a fixed number of trials, that's what n represents, the probability of its success being provided, and how many successful outcomes are you looking for. So that was just kind of how to use the table. So now kind of exposure to the formula. This is the formula for a binomial experiment, which yields the same values of the table, but the table, if you notice, only gives us certain values for p, for the probability of success, only these numbers. So if I wanted to determine in 2 trials if the probability of a success was 0.29 and was 1 success, I can't use this table, right? It's only for these fixed values here for the probability of success. So therein lie an issue if we want to calculate that probability. So we would have to use something different, which would be the formula here. Now in the formula, there is some information that is not new to us, which if you notice this part of the formula where it has the n factorial divided by n minus x factorial times x factorial, that's our combination friend from chapter 4 paying us a visit. So we've already been able to calculate that. We know how to find that value, but I'm going to show you a little easier way to obtain that value in this section, since more or less you're not being tested on like you were in the previous unit. Do you know the difference between a combination and a permutation? It's can you just find that value to help you calculate the probability of your of this number of successes. P is the probability of it. P is the likeliness of its success, and Q is the likeliness of a failure. So we look at in our formula here, we have P is the successes and Q is a failure, which you can arrive at that value by taking 1 minus P. So I'm going to show you what I mean, more of like an application type problem. I'm going to take those same examples we looked at previously, and I'm going to use the formula now to calculate the binomial probability using the formula, so you can see that whether I use the table because these values are in the table, or whether we use a formula, it gives us the same information. So if I wanted to calculate the probability of one success in a 2-trial experiment where the probability of its success was 0.30, well, I would set this up as 2 choose 1, because that's part of the formula that I would like to figure out what that value is, times, so here's my 0.30, and then in the formula it was to the x power. Well, x is 1, and then Q is the probability of a failure. So if this is 0.30, which is the probability of a success, then a failure would be 0.70. These two things have to add up to 100%. And then that would also be to the first power, because this was n minus x. So either you look at it as subtract these two numbers to get this value, or the two exponents have to add up to the number of trials, because it's this many successful outcomes and it's this many non-successful outcomes. And then to actually calculate that value, and for that I want to use Desmos. And I didn't show you this before, which I could have shown you this in chapter 4, but I wanted you to at least be able to calculate it by hand. In Desmos, you can type in NCR. So you have to type in lowercase n, capital C, lowercase r, parentheses, and then we have 2, 1, and that will do the same evaluation that we did by hand, which would have been 2 factorial, 2 minus 1 factorial times 1 factorial. So that's the same calculation, which is 2, and we need that value so we can calculate the probability. So I know that 2 and then times 0.30 raised to the first power, and then times 0.70 raised to the first power is 0.42. So essentially that's the same value that we found before from the table. So I go back here, that value is 0.42 for the probability, which is subsequently the same value that we got in the table. So if I go back to the table here and I go back to n equals 2 for one success and 0.30, 0.42, if we just leave off that extra 0 at the end. So it gives us the same value. Now let's look at another example. So for the second one, I want the probability of 3 successes. So if I set this up, we have 4 choose 3. So n is 4, x is 3. The probability of a success was 0.60. So we have 3 successes for 0.60, which means for a failure would be 0.4, because if 60% of the time we expect a success, that means 40% of the time we expect a failure. And if there's 3 successes out of 4, that means there will be 1 failure out of 4. And again, if I go to my Desmos, NCR, 4 choose 3, so that's 4 outcomes. 4 times 0.60 raised to the third power, and 0.40 raised to the first power. And essentially it's the same value that we found before. So if I go back to the table, which is 4 successes, 0.6, and we go, or 4 trials, 3 successes, go over to 0.6. So notice this value is rounded. Every value in the table is to the 3rd decimal place. And if I look back at Desmos, it gives me to 4 decimal places. So if we round it, it gives us the same value, 0.346. So that's what we get for that one. And I'm going to skip over the second one, just go to number 10 in the interest of saving a little bit of time. So probability of 4 successes in a 10 trial binomial experiment So 0.40 would be my probability of success. There's 4 of those outcomes. And then 0.60 would be my probability of a failure. There will be 6 of those outcomes. And then to evaluate that, go over here. So NCR 10, 4. So 10 choose 4. So there's 210 outcomes. 210 times 0.4 raised to the 4th power, and then 0.60 raised to the 6th power. And if you notice, we get 0.251 essentially. If I go back to the table, if I go to n equals 10, we have 4 successes, and we go over to, I'll assume it's here, let's see, 0.4, so 0.251. So we get the same value as we got before. So that more or less, whether you use the formula or the table, you get the same values. However, the table can only be used for certain probability of success values, while the formula can be used for any value. And we'll look at that in some application problems. So let's look at an application problem and see how we could utilize the table versus utilizing the formula. So in this particular problem, it says a missile guidance system has 5 fail-safe components. The probability of each failing is 0.05, and we want to find these probabilities. I want to know the probability that more than 2 of the components will fail, and then I want the probability that exactly 2 components will fail. So first we look at the 5. Well, that in essence is a fixed number of trials, more or less. And the probability of each component failing is 0.05. So each of the 5 components has the same likelihood of failing, a 5% chance. And so this satisfies that binomial setting, because for one, there are 2 outcomes. They either will fail or they won't fail. So that's 2 outcomes. There's a fixed number of trials. There's only 5 components. There's not an infinite number of components in this missile guidance system. The probability of each component failing is the same, and the components should be independent of each other. So this satisfies those 4 conditions. Now, you don't actually have to confirm that in your homework or anything, but that is something you want to kind of think of. Well, what are the 4 things, can I identify those 4 conditions within this problem to see if it satisfies the binomial distribution? And this one does. So now we're thinking about our statement here. Well, also the 0.05, that's my probability of success. So that would be like my p-value. So in this case, x, if we think about more than 2 will fail, that means 3 could fail, 4 could fail, or 5 could fail. And if we remember back from when we first began talking about probability, the word or kind of tells us that we were going to add the probabilities together. So we add each of the probabilities of x together. That means to find the probability that more than 2 will fail, I need to find the probability that 3 will fail, plus the probability that 4 will fail, plus the probability that 5 will fail. Now, we can use the table, right? This number is in the table, the 0.05. So that tells me if it's in the table, I can use it. So if I go to the table, I'm looking for n equals 5, and I'm looking for 3 successes, 4 successes, and then 5 successes. So if I go to the table and I go to n equals 5, so here's n equals 5, and here's 0.05 in the table. We have 3 successes, 4 successes, 5 successes. The probability that 3 components will fail, according to the table, is 0.001, less than 1% chance, a 0.1% chance actually. The probability that 4 will fail is blank, so essentially is 0. The probability that 5 will fail is also blank, so essentially is 0. So when we go back to our problem here, the probability that 3 will fail, 0.001, probability that 4 will fail, 0, probability that 5 will fail, 0. So when we add these numbers together, we get 0.001, which is a very unlikely that more than 2 of the components will fail, because if we think about it, there's only a 5% chance that each one fails. So what's the likeliness of more than 2 of them failing? That should be very low, because it's only 5% of the time, 5% of the time they will fail. Now, if we look at this kind of to confirm it, we could also use the formula for this. And so for that, I'm gonna go back to Desmos to kind of show you here. So NCR, 5 components, 5 choose 3. And you can actually type everything at once. So you don't have to really type this separately. Now I can type in 0.05, the likeliness of a component failing raised to the 3rd power, because we're looking for the fact that 3 fail, times 0.95. So if there's a 5% chance it will fail, there's a 95% chance that it won't fail, raised to the 2nd power. So we have to keep in mind that the exponents have to add up to the number of trials, which is 5, and the percentages have to add up to 1, which is 100%. So failures and successes. And notice this is the same value from the table. Now, I'm pretty lazy, so I like to copy and paste a lot of stuff, so I just copied and pasted it. And for 4 failures, just change this to a 4. That means I change this to a 4, and we change this to a 1. And this is essentially 0. It's a small enough number that when it rounds, it was 0 in the table. Same thing with the 5. So if I go back, change this to a 5, this would be 5, and this would be 0. So this is an even smaller number because it's 10 to the negative 7. That means you take this decimal point and you move it 7 places to the left. So when we add those values together, we still get the 0.001, much like we got in the table. So you see you have some flexibility in your homework, and I believe you have one similar to this. You will be able to use the table for the application problems for some of them, and some you'll be able to use the formula, or you can use a formula for all of them. But you have that. If you can use the table, I would encourage you to try it, because you will find success with it. So the probability that exactly 2 will fail, well, that just means probability of just 2. In this case, we would set it up like we did before, 5 choose 2 times 0.05 to the 2nd power times 0.09 to the 3rd power, and then we could either use the table for that. So let me go back, let me go to the table. So 5 trials, 2 successes. In this case, the successful outcome is that it will fail. And really, I don't want you to have the mindset of success in this case means something good. It's just the outcome that we desire. In this case, the 0.05 was about the component failing. So that in essence is our success. And then the failure would be not failing. But you can do it both ways actually. But we go to our table, 5, 2 successes, and we go 0.05. So 0.021 is the value I get from the table. If I go to Desmos and let me continue with my copy and paste, this would be 2, this would be 2, and this would be 3. So 0.021, same value. So we have some options that we can kind of work with here. So the probability that 2 will fail is 0.21. And again, that's an unlikely event. 2% chance that 2 of them will fail. So let's look at another example. We have, this is the second example of applying the binomial probability. So each student takes a 20-question multiple choice exam with 5 choices for each question and guesses on each question. Find the probability of guessing at least 15 out of 20 correctly. Would you consider this event likely or unlikely to occur? So first, we have to consider, does this represent a binomial distribution? Does it satisfy those 4 requirements? So first requirement, there is a fixed number of trials, right? There's only 20 questions. You're not, at some point, the test or the exam will end once you finish the 20th question, once you finish guessing the 20th question. There are 2 outcomes. You either guessed it correctly or you guessed incorrectly, right? Those are only 2 outcomes. The probability of each trial, so in this case, each question is the same. If there's 5 choices, that means you have a 1 in 5 chance of getting it correct. So is there a 0.20% or 0.20 or 20%? And the trials are independent, because if you're guessing, then my first guess has no effect on my second guess. Maybe, I mean, more or less, it shouldn't have an effect because you're just purely guessing. So this does satisfy those 4 requirements talked about earlier. So we look at, well, n is 20, probability of a success is 1/5, our 0.20, and then x we can consider is the number of the number of questions we guessed correctly. That's what x represents. And so we want to find the probability that the number of questions we guessed correct is greater than or equal to 15. It says at least 15. So that means we want the probability of 15 or 16 or 17 or 18 or 19 or 20 questions guessed correctly. And when we think about this problem, we could use a formula here, right? We would just have to use it 6 different times. We could also use the table because this value is in the table. So you always want to check if the probability of the success given to you in a problem is in the table. In this case, it's in the table. So I might want to go that route instead of having to use the formula 6 different times. Although it may not be too terribly difficult, it is definitely tedious. So I want to go to 20, which is on the last page. And so here's n equals 20. And we have a 0.2 or 1/5, 20% chance. So 15, 16, 17, 19, 20. If I look, it's all blank. It's essentially 0. So when I go back to my problem here, the likeliness of someone guessing at least 15 questions correct out of 20. So that means they would guess all 15 are 1 through 15 correct, or 1 through 16 correct, or 1 through 17 correct, or 1 up to 20 is 0, right? According to the table, that's an impossible outcome. It's not going to happen that someone guesses at least 15 questions correct. That means minimum they have to guess, purely just bubbling in answers, 15 questions correct, which is not going to happen. Now we can use the formula for this as well to kind of show the same value, but I want to show you probably a little easier way even to get the value that we need, especially because there's 6 different probabilities we have to calculate. So in Desmos, you can pull up a feature known as a distribution. So you have to click down here, the little keyboard, and you have to click functions, and you click on distribution, and you click on binomial distribution. And it's going to say in parentheses here, it says trials, comma, successes. So 20 trials, comma, trials, comma, success probability. So I can put 1/5. Now notice it makes a kind of a dot plot of the different outcomes. So if I go over here and I find 15, so here's 15, 16, 17, 18, 19, 20. The first value in the ordered pair is the x value. So when there's 15 successes, the probability is 0. So you could do this as well to get the numbers even quicker. And then down here, if I click on find cumulative probability, so from 15 to 20, it tells me that the sum of these values is 1.8 times 10 to the negative 7. So that's a really small number. You take that decimal point and you move it 7 places to the left, and 0.00000018, so essentially a 0. So that's another way in which you can also find the probability for a binomial distribution, even easier in your calculation. All right, let's look at our last example, high school dropouts. High school dropouts, so approximately 10.3% of American high school students drop out of school before graduation. If we choose 10 students entering high school at random, find the probability of that, and we look at these 3 cases. So again, it satisfies the 4 conditions. There's a fixed number of trials. We're choosing only 10. We don't have access to an unlimited number of students, so we're only choosing 10. There's 2 outcomes. You either drop out or you don't. The probability of dropouts is the same throughout. It's the 10.3%, and it's independent of each other. Student dropping out this should not affect another student dropping out, more or less. I know when I dropped out of high school, I don't think anybody dropped out because I dropped out. So it was my own choice, and that was that. But look, now I'm here. So Now we want to determine, well, that's our p-value. Well, that's the probability of success, 0.103, and the probability of a failure is 0.897, right? So that's would be graduated, whereas the other one is dropout. And here, since we want to find the probability that no more than 2 drop out, well, we could say X, for this example, we could say X is the number of dropouts, and no more than 2 means 2 or less. So what we would like to determine, what's the probability that none dropped out, that 1 dropped out, and that 2 dropped out. Now for this, we would most definitely have to use a formula because this value is not in the table. So unfortunately, we would want to use a formula here. All right, so we can set this up, and then we would have to enter this in Desmos, but I'm going to show you the 2 ways. I'm going to just reiterate this formula. So NCX, N is the number of trials, X is the number of successes. So for this particular part, we have to find all 3. So no successes, 10 trials. This is the probability of a success. So in this case, since 0 represents no dropout, the first number has to be related to dropping out, which is the 0.10. And then if none of the students dropped out, that means 10 of the students graduated. So the second value represents graduated, 0.897. So those values have to be related to each other. 0 students dropped out, the likeliness you dropping out. 10 students graduated, the likeliness of you graduating. So those have to be correctly done in the formula for us to get the correct value. So if I go back in here, and I'll just delete this other work. Probably should already did that. All right, so we want NCR 10, 0, and then 0.103 raised to the 0th power because none dropped out, and then 0.897 raised to the 10th power. So that's one of the values I need. It's not the only value I need, it's one of the values I need because we got to find the other 2. So the next one is a probability that 1 student dropped out. Notice the change in the formula. We have, well, I'll go ahead and give you the answer there, but I'll still type it in. So 10C1, so now 1 dropped out. So in our formula, this exponent changed to a 1 because now 1 student dropped out, and then this changed to a 9 because if 1 drops out, that means 9 now graduates. And so when we go back over here to Desmos, I can copy this, and then really I just change the numbers around. 1 and 1. And notice the probability changes. It's a little higher percentage for 1 student dropping out. And we go back and we repeat the same process for the last value for 2 dropping out. So notice again the change in the values. The only thing changing here, I'll go ahead and give that to you. So the only thing changing here is the value of X. Right now X is 2, so 10C2 stays the same to the 2nd power, stays the same to the 8th power. Each time the exponents, they add up to the number of trials. So 1 plus 9 is 10, 2 plus 8 is 10, and then these values, essentially they stay the same. They should stay the same. So when we go back to our Desmos here, and that is going to be 8, 2, and this will be 2. So now we have each of the probabilities because of the statement or. So you have no dropout or 1 dropout or 2 dropout. We just add those values together to get the overall probability. Now you can use the distribution as well that I showed you. So if I go binomial distribution, 10 is the trials, the success 0.103, and I can just, honestly, you could click on here. So no dropout, 1 dropped out, 2 dropped out, and if I wanted to add it for me, I just go from 0 to 2, and it adds it. It adds those 3 values together. You can even see them highlighted up here in the Desmos. Now, so I want to show you both ways, kind of give you all your options, more or less. But that's the pretty high likeliness that no more than two students drop out. So if you chose 10 students at random, there's a 92% chance that no more than 2 of them are going to drop out. And hopefully that makes sense, because 10% of the students, 10% of all high school students drop out. So if we, and in comparison to the 10 that you choose at random, 10% of the 10 would be one student. So the likeliness that no more than two, like at most two students, that should be a high chance, because we're looking at anytime we have or, probably that none drop out, or one could, or two could. We're adding those together to increase the likeliness of the event, when each separate event itself is not too terribly high. So 33% chance that none drop out, 39% chance that one drops out, and then 20% chance that two drop out. So for the second example, we look at least 6 graduate. I'm gonna look at this two different ways. So this time we could still say that X was the number of dropouts, but I'm going to change it to say that X is the number of graduates. So we're going to mix up the values for P and Q. So what does at least mean? It means that number or greater, which means I want to find the probability of 6 or 7 or 8 or 9 or 10 graduated this time, not dropped out, graduated. So when we think about what we've already found, 3 of the numbers we already know. So I'm writing it this way. If 10 students graduate from high school, then we have to think about, well, that's the same as no students dropped out, which we've already found that. If 9 students graduate, well, that's the same as 1 student drops out. So we've already found that. And if 8 students graduate, that's the same as 2 students drop out. And so we've already found those values. So I don't have to find these again, because I've already found them. The probability that 10 students actually graduate is the same as the probability that no students dropped out, which we found that in the first example. And then, so we found those, we already know those values, right? I can write those down already because we already found them. I'm going to show you that they're the same too. So if I go back to here, now keep in mind, I have to change up my numbers. So, and that's why I have to change up my numbers, because this distribution here is only based on the percent of dropouts. Because now I've changed the parameter and I've said that X is the graduates, I now am going to change this distribution to still 10, but this time 0.897, and I'm going to hide this. And so 10, that's the same as 1. So if 10 graduate, I guess I'll bring it back. I mean, if 10 graduates, that's the same as no dropout. If 9 graduate, that's the same as 1 drops out. And if 8 graduate, that's the same as 2 drop out. So we have to consider that if we change what X represents, then I also have to change what the success probability is, because I'm no longer saying that X is the number of dropouts with this second part of the problem. I'm saying that X is the number of graduates. So I have to change it up. And that means that when we look at our formula now, if I were to write out the formula, I change the order a little bit. So 10 choose 6, because now 6 is the number of graduates. So this is the percent who graduate. So that's why the 6 is with this number. And that gives us 0.012. And then if 7 graduate, then that gives us 0.61, which is an almost 100% chance that at least 6 graduate, almost, but not entirely 100%. So if I were to go back to Desmos and use my cumulative distribution on this from 6 to 10, right, 0.998, this numbers. Now, if at least 6 student graduates, that's the same as saying no more than 4 students drop out. So if I put a 4 here, oh, not 24. Notice they're the same value, right? Because if at least 6 graduate, so if I go back, if at least 6 graduate, that's the same as saying no more than 4, because this is no dropouts, this is 1 dropout, 2 dropout, 3 dropout, 4 dropout. So we can think of it several different ways.